we go. So today we're going to be talking about weather. So this week the targets were all about weather and kind of going with what we've already discussed in class about, how different systems of Earth interact. So weather is a big part or a big reaction or a big system that occurs because of those interacting systems with the hydrosphere and the geosphere and the biosphere and all those things. So today we're going to kind of go over how weather works, some different wind patterns that we see on Earth. We'll just start kind of the first half since we don't have the whole period today. I just want you guys to go through the first half and then we'll stop there. And then tomorrow we'll kind of finish up. I'll have another screencast for you guys tomorrow, and you can use that to finish your notes, and then we'll have a little activity after that. So to start with, lecture 3B. So 3B this week, that's our target set. You should talk about the targets yesterday. Today we're going to be, like I said, kind of going over different weather patterns. Just kind of take notes. There will be some drawings that I want you to have in your notes this week to help you. You should transfer those to your targets so you guys can get those done at a high level. So to start, the target at the top left-hand corner, we're going to be able to explain the effective properties of water on energy transfer. We'll also talk about properties of gas. We'll discuss that a little further. That causes the patterns of temperature, the movement of air, and the movement and availability of water on Earth's surface. So when we talk about water moving, how that affects the air above it, and things like that. So when we talk about currents of the ocean, that directly plays a part in the air that we see, the movement of the air above it, and vice versa. The movement of the air can also influence currents of the ocean. So we'll kind of cover that briefly. To start with, though, we're just going to go into basics, discussing the difference between climate and weather. So we'll talk about weather first, and then we'll get more into climate. I'm sorry, we'll talk about climate first, and then get back into weather. Okay? So first of all, when we talk about climate, you guys had 2 articles yesterday that went through climate and weather. But climate is long-term. It's one thing you just need to make sure you understand. So we're looking at the average temperatures for a particular area or a particular place on Earth for 30 years or more. So according to the World Meteorological Organization, WMO, this is their definition of climate. So average temperatures and weather patterns that we see in a particular place for 30 years or more. Vladimir Köppen and Rudolf Geiger divided the world's climates into categories based on general temperature related to the latitudes of Earth. So when we look at Earth, we can divide it into different latitudes. And so with that, and the latitudes are the ones that are going to run east to west. So those lines on the globe that run east to west, with the equator being at 0 degrees latitude. If we go below it, so it goes in 10 degrees kind of sets. And if we look at it, those different lines of latitude, we can determine, or we can usually see patterns of the types of climates that we see in those areas. So obviously along the equator, we're going to have higher temperatures, more moisture in the air. As we get further north, a lot lower temperatures, a lot drier air as we get further and further away from that direct sunlight, and therefore less moisture being put up into the atmosphere. Okay, so we have different climates, like I said, based on how far you are away from the equator and how close you are to the poles. Okay, so here's some things about the lines of latitude. Another way that we describe them, they're also known as parallels. Again, they kind of run parallel to that equator, and they run around the entire Earth. Okay, so from 0 to 90 at the very top, that would be our 90-degree line of latitudes. You can see if you're sitting right at 80 to 90 degrees latitude, you're at the very top or the very bottom of the Earth. Okay, like I said, they run in east to west direction, so they're running horizontally, I guess you could say, around the Earth from east to west. They measure the distance north or south from the equator. So if someone says, I'm 20 degrees north, that would tell you that their latitude is 20 degrees, so they're sitting right along that latitude line. Okay, and it runs through the Pacific through the Atlantic right there, and the Pacific is going to run all the way around. But it also, you can see if you're at 20 degrees and you're on land, you could be in Africa. You could also be in, towards the bottom of North America. Okay. They cross what we call the prime meridian at right angles. So the meridian lines run north to south. So they're going to run into each other, and that's how we kind of use those lines of latitude and longitude, or the meridian lines, to determine where you are on the Earth. Okay. They lie in planes that cross the Earth's axis at right angles. So if we were to cut the Earth in half, we could see that those lines of longitude or latitude would go right angle to the axis of the Earth. And because the Earth is a sphere, those latitude lines, they are going to get shorter as we get closer to the pole. The longest one makes sense because it's the middle of a sphere is the equator. So the 0-degree latitude line is going to be the longest line of latitude on Earth because it's directly in the middle. It bisects the Earth in half. So above that 0-degree latitude line would be the northern hemisphere. Below it, we would be talking about the southern hemisphere. So some interesting things. And again, we use these lines of latitude to also give us a feel for the different patterns of weather that we're going to see based on where you're found as far as degrees of latitude around the Earth.
Being hunted down by a robot.
If we look at this picture, this is showing
just got
the different seasons.
Terrifying.
And you can see the tilt of the Earth and the amount of direct sunlight showing.
Smart device required. Ask your parents before downloading the free app.
Tilt, showing the direct sunlight, and also what season we're going to be in as the Earth circles around. So September 22nd, we have our winter solstice. Again, that's if you're in the northern hemisphere.
All over the world is caused by heating and cooling of the Earth.
Away from the sun.
Wind can do work.
We're looking at June 22nd.
And it makes
you can
sailboats.
see that's our summer solstice. So our days are really long because we're getting a lot more direct sunlight in that northern hemisphere. So it would be the opposite if we were to look at this and we were looking at the southern hemisphere. So look at the December 22nd. Now the bottom of the Earth is tilted more towards
The real
sunlight,
wind doesn't
so
come
they're
from
gonna
a
be actually
fan.
more in their summertime,
No, in nature,
summer season,
wind is
as
caused
opposed
by
to
the
winter.
heat
So it's
from the
opposite
sun
based on which
and the
hemisphere the Earth
rotation
is in.
of the Earth.
Again,
That's what makes these intricate
lines of
patterns
latitude
of
also
clouds that we
for
see
that.
on this photo from space. It works something like
climate.
this.
So these are
This
different
is our
tropics,
great
different
big plastic
climates that we see
wind
on
box
Earth.
of science.
So, there are
These
other
lights
ones,
represent
kind
the
of the main
sun.
ones. So we
This
look at
ice
tropical
represents the
climate,
north and south
tropical,
poles.
a lot of moisture.
So here's what happens.
Sunlight.
Energy from the sun heats the land, and the
A lot of
land
weather, a
warms
lot
the
of
air
rain,
over
a
the
lot of
land.
moisture, like I
Air
said
molecules
here.
get going
We look
faster.
at dry
They spread
temperatures,
farther
that's
apart,
associated with
so they don't
more
weigh as
desert
much for the room they
areas.
take up. So cold air
not
can
nearly
push the
the amount of
warm air
moisture
up.
in the air.
That's why we say warm air
hot,
rises.
dry.
So look what's happening. The smoke
A lot of
shows
weather
us that
associated
the air is
with
sinking over the cold poles, flowing
Subtropical
over the
mid-latitudes,
cities,
so
and
moist,
then rising
obviously,
over the
we're gonna
warm
see more
parts.
of those.
See, it goes around in a
Where's
great
more
big
moisture
circle.
in the air, so
And that's what happens on the Earth. Now there's one more
towards
thing.
more towards
The Earth is
equator.
spinning,
Same thing with
so the wind
continental
starts spinning.
latitude.
That's why wind comes from all
the,
different directions.
you know,
Wind is
land,
wild.
Polar. Now we're going up towards those really high latitude lines of latitude. So we're up around 70, 80, 90 degrees latitude, and on both sides. So even in the south hemisphere and the north hemisphere. So we're going to see, a lot colder temperatures because it's not getting as much direct sunlight. We're not going to see as much moisture in the air because there's just not as much water in those areas. So we're going to see a lot more of that energy from the sun also being reflected, so it also stays colder in that way as well. So it's not absorbed by the parts of the Earth where we're finding that sunlight. Okay. These are areas where we have seen similar types of weather patterns and temperature over extended periods of time, so 30 years or more. So these are just some of the more identifiable types of climates that we see on Earth. Okay, and a lot of times when you hear climate, you can also think of them being associated with different biomes on Earth. When we look at biomes, we're adding the organisms that also are going to be found there. So when we talk about biomes, one of the main things that we look at is the climate of those particular areas. So, and then the organisms that are able to survive there. So some are very harsh, some not so harsh, some a lot. Some can support a lot of life. Like if we look at the tropics and we look at rainforests, we're going to see a lot more different species of organisms being supported. There's just a lot more energy. There's a lot more sun. We look towards the poles, not as much energy available, not as nice of conditions, quote unquote. Not a lot of different species of organisms are able to handle those types of conditions. Okay, so weather. So on the other side of that, we're looking at weather. So weather is the current state of the atmosphere. So we're looking at 3 different pieces of weather, and I'm going to go into detail. Today I'm just going to stick with wind. I'll get to temperature and precipitation tomorrow. But one part of weather is, the wind on a daily basis. If you were to watch the news in the morning, one thing they're always going to be talking about, or they're usually going to mention, is what is the wind going to be like? Is there going to be wind? Is it going to be strong wind? Is it going to be light wind? Okay, so I want to make sure that we understand what causes wind and why we see different wind patterns all throughout the earth that are pretty constant. Okay, so I'm going to have you watch this quick video. Just take some notes on it. Bill Nye kind of goes on a little bit about how wind forms on different parts of the earth. So why we see in some areas very strong winds, and then what the main reason is for wind being created. So
jet streams are another name for fast-flowing currents of air. There are many different jet streams that exist at both high and low levels in the atmosphere. Each has an important role to play in the weather experienced on Earth. The major jet streams that circle the Earth are found just below the tropopause at a height ranging from 9 to 16 kilometers and can reach speeds over 200 miles per hour. They are hundreds of kilometers wide, but only a few kilometers deep, so are often described as a ribbon of very strong winds. The major jet streams are the polar front and subtropical jets. These occur in both the northern and southern hemispheres and are part of the larger global circulation. The polar front jet occurs over mid-latitudes and strongly influences the weather over the UK and Europe. The polar front jet is a type of thermal wind that arises due to the strong temperature contrast between cold polar air and warm tropical air. To explain this further, imagine 2 columns of air, one in the cold air to the north of the jet and one in the warm air to the south. The top of each column is bounded by the tropopause. A shorter column of cold air exerts the same surface pressure as a taller column of warm air. This is because in the cold air column, the air is more dense. This causes atmospheric pressure to decrease more quickly with height. In the warm air column, pressure does not decrease as rapidly with height, because the warmer air is less dense. The tropopause in both columns is at the same atmospheric pressure. So if you were to climb to the same height in both columns, you would find that you would be at a lower atmospheric pressure in the cold air column and a higher atmospheric pressure in the warm air column. The pressure difference caused by this temperature gradient produces a pressure gradient force. The pressure gradient force acts from high to low pressure, so theoretically in the northern hemisphere,
wind,
air would flow
moving air
from south
caused by
to
uneven
north.
heating of the surface. So what Bill was saying in that video, he showed
But
that
the
some areas
Coriolis
are
force
receiving more
resulting
heat
from the Earth's
than
rotation
others.
causes the air to move to the right of the direction of motion in the northern hemisphere and to the left of the direction of motion in the southern
So because of
hemisphere.
that, the Earth's surface is
In both
is
hemispheres,
heated
the
unevenly.
jet stream flows
So
parallel
hydrogen
to this
rise,
temperature
it
gradient,
creates what we call
moving
that
from
low
west
pressure.
to
So those
east.
molecules,
Theoretically, this jet
standing
encircles the
out,
Earth
they're not going
in
to
a
be
continuous
They're going to
line,
be more spread.
but in
more
reality,
energized.
it is
If you
more
think about
broken
cold
up.
air, it's going to sink. We
as
have
differential
areas of high
heating of
pressure.
land sea masses lead to west to east temperature contrasts as well as north to south.
So air always moves from
As
higher
the polar
pressure
front jet
to
forms
lower
due to the
pressure.
temperature contrast,
Okay, so
the stronger
hot
the
air is
temperature
going to
gradient, the stronger the
rise.
jet. This means that the
And
jet
that's
is
actually
stronger in the
backwards. So
winter
hot air is
than the
gonna rise,
summer
it's gonna
as the
create-
poles cool during
Oh, no,
the
that's right.
winter
It's gonna be
months,
low pressure
increasing
and
the temperature
so low
contrast.
pressure as
In the
it's
northern
higher up,
hemisphere,
because
the
it's
jet
gonna
tends to
be
be
less
further south in
dense.
winter and further north.
cold air is going to sink. It's going to be more dense, higher pressure. Okay, so I want you to draw this diagram in your notes. This is showing the different types of air that we're going to see in our atmosphere. So creating these different types of prevailing winds, and we have the different cells. We talked about those a little bit before. So we have the Hadley cells, where we're going to have a lot of warm air rising. Okay, and it's going to circle back. So there's our convection cell. And then when we go to the 30 degrees north latitude, so above and below, we have those Ferrel cells. So we're going to see that polar jet kind of interacting with those, and then we have the polar cell as we get towards the poles of the Earth. Okay, so those are 3 cells. I want you to draw this in, and then also don't forget the bottom part. I want you to draw the jet streams. We're going to talk about those next. In there, you can see the jet streams on Earth. You can see that they circle the Earth, and that's what we're going to focus on next. But these are the cells that we see because, again, of that uneven heating, and then also because of the spin of the Earth. Okay, so here's a little video on jet streams. I want you to write the question down. According to the video, when are the jet streams of Earth usually the strongest? And then I want you to tell me why. So it's a pretty lengthy video, but it's going to kind of go into the jet streams, what they are, how they're created, and then when they're going to be the strongest, and then I want you to tell me why that happens.
Jet streams are another name for fast-flowing currents of air. There are many different jet streams that exist at both high and low levels in the atmosphere. Each has an important role to play in the weather experienced on Earth. The major jet streams that circle the Earth are found just below the tropopause at a height ranging from 9 to 16 kilometers and can reach speeds over 200 miles per hour. They are hundreds of kilometers wide but only a few kilometers deep, so are often described as a ribbon of very strong winds. The major jet streams are the polar front and subtropical jets. These occur in both the northern and southern hemispheres and are part of the larger global circulation. The polar front jet occurs over mid-latitudes and strongly influences the weather over the UK and Europe. The polar front jet is a type of thermal wind that arises due to the strong temperature contrast between cold polar air and warm tropical air. To explain this further, imagine 2 columns of air, one in the cold air to the north of the jet and one in the warm air to the south. The top of each column is bounded by the tropopause. A shorter column of cold air exerts the same surface pressure as a taller column of warm air. This is because in the cold air column the air is more dense. This causes atmospheric pressure to decrease more quickly with height. In the warm air column, pressure does not decrease as rapidly with height because the warmer air is less dense. The tropopause in both columns is at the same atmospheric pressure. So if you were to climb to the same height in both columns, you would find that you would be at a lower atmospheric pressure in the cold air column and a higher atmospheric pressure in the warm air column. The pressure difference caused by this temperature gradient produces a pressure gradient force. The pressure gradient force acts from high to low pressure, so theoretically in the northern hemisphere air would flow from south to north. But the Coriolis force resulting from the Earth's rotation causes the air to move to the right of the direction of motion in the northern hemisphere and to the left of the direction of motion in the southern hemisphere. In both hemispheres, the jet stream flows parallel to this temperature gradient, moving from west to east. Theoretically, this jet encircles the Earth in a continuous line, but in reality it is more broken up, as differential heating of land-sea masses lead to west to east temperature contrasts as well as north to south. As the polar front jet forms due to the temperature contrast, the stronger the temperature gradient, the stronger the jet. This means that the jet is stronger in the winter than the summer as the poles cool during the winter months, increasing the temperature contrast. In the northern hemisphere, the jet tends to be further south in winter, further north.
Okay, so hopefully you got that answer. I didn't mean to stop it so abruptly, but hopefully that answer. I want to go back real quick. So when we think of cold air, I want to make sure that these are switched. So hot air rises, we're going to get high pressure when we think of hot air, and then cold air, we're going to have low pressure. Okay, so when we talk about a low pressure system and a high pressure system, hot air is going to have the higher pressure. So I want to make sure we have that. And then air is always going to move from high to low. So that video really did a good job showing how that movement of air would naturally go from high to low. So in the northern hemisphere from south to north, because of the spin of the Earth, it's going to shove it to the right. So it's going to move from that west to east direction. Okay, so make sure you switch those. So right here where it says low pressure and this is high pressure, those should be switched. So hot air does rise, but it's going to create that high pressure. Okay. Okay, so those are jet streams. Again, they're narrow bands of winds. They're fast moving. They're high above the earth. They're going to be right at that tropopause level. So they're going about 145 miles average, depending on the time of the year, the seasons, which we just talked about, and the uneven heating. They go from west to east, but they do kind of flow north and south as well. So they'll shift based on, again, the different temperatures that we see of the land or what we're flowing over. So a lot of times you'll hear, if you're going from west to east, you're going to hit that jet stream possibly if you're flying along the northern part of the United States, and that could cause your trip to go a lot faster. When you're coming back the other way, you might be fighting that jet stream, those jet stream winds. Okay. Again, they follow the boundaries between the hot and cold air, so moving from around the earth. Okay. They're going to follow the sun. Elevation increases in the spring, latitude shifts poleward, so that air temperature is going to get warmer in the spring to summer. By summer, the northern hemisphere is typically found near the U.S.-Canadian border, so it's going to shift that jet stream further north. In autumn, fall, and so that fall time, winter time, that sun's elevation decreases, so the stream average latitude moves more towards that equator, or towards the equator. Okay, and so there you go. With their elevation, you can see how it's also going to shift and move further north as we get higher up in elevation. Okay, so that's where we're going to find more of our jet stream. Trade winds. So another type of wind system on Earth that is pretty constant are what we call the trade winds. It's a steady warm air that blows toward the equator between 30 and 0 degrees latitude. Again, the equator is 0 degrees. So, 3 lines of latitude above and below the equator would be that 30-degree line. Where trade winds meet, there's a calm area where we're not going to see much wind. That's called the Intertropical Convergence Zone, or ITCZ. Okay, and here's a little map. So when we have that meeting of those trade winds on the north and south hemisphere, where those meet, we're going to have a nice little band there because they kind of cancel each other out. Okay, so trade winds. You can see because of the spin of the Earth, we're going to see those winds, in the north moving more of that clockwise fashion, and the south is going to be moving more of that counterclockwise fashion because the Earth is spinning. Okay, prevailing winds. They're deflected because of the spinning of the Earth as well, the Coriolis effect. So it's deflected to the right in the north. That air is going to be deflected to the left in the south. They blow from one direction in the same area of the world, caused by rising heat from the equator again. These ones are going to travel toward the poles, so that air traveling towards the poles from the equator. So we have the westerlies. Okay, so this is they blow from west to east. Again, kind of like our jet streams as well. They're between 30 and 60 degrees line of latitude, and then the polar easterlies between 60 and 90. Okay, so polar easterlies are going to blow from east to west. Okay, that's another thing about wind when we're describing it. If we say it's a west wind, that means it's coming from the west. If we say it's a north wind, it's blowing from the north. If we say it's an east wind, it's blowing from the east. Okay, so these are just two types of what we call prevailing winds to go along with the other wind types that we have again on the Earth. And again, the Coriolis effect plays a huge part in how these winds travel across the surface of the Earth. Okay, here's a nice little diagram to show all these different types of winds. So because of the movement of the air traveling from the equator, and then that polar air also converging with it, and the spin of the Earth, we're going to see these winds go in the directions that they go. And again, so here's you can see up towards this area, so down towards the equator, here's our trade winds. Okay, it's deflected to the right, and so it's going to go in this direction. In the bottom part, again, because the Earth is spinning, so you can kind of see how it moves in a circle. So here's our westerlies. So they're moving up, and they're going to go more towards west to east, similar to our jet streams. And then here's our polar easterlies, that cold air coming down, and it's going to shift it towards the left in the northern hemisphere. If you look in our atmosphere, the different cells, so the Hadley cell, here's our subpolar cell, and then the other cells of weather that we're going to see based on wind and convection currents from the equator out and working its way up. Okay. Local wind, so movement of the air influenced by the surface features. We're going to have, different topography in the areas that we are. In California, we have kind of mountains on either side, so that greatly influences the winds that we see. Also, at the ocean to the west, so as that warmer air possibly moves over those mountains, we're going to see different pressures, different air pressure associated with it. Again, if it's high pressure, it's going to want to go from high to low. So a lot of times we're going to see that wind. Gentle winds, kind of, when we see those, we call them breezes, but they're just going to be kind of left remnants of air movement, just small pockets where we're going to see movement of air from that high to low pressure. San Diego is influenced by sea breezes and westerly winds, again because of the ocean where it sits. We're going to see those slight breezes and then also those westerlies because it's right on the coast, right over that. And again, more uneven heating. Okay. One local wind that we can use for example in California, the Santa Ana winds. Okay, these are dry and warm, often hot winds that blow in from the desert. So they're going from that high pressure system, high pressure areas, and then they're going to be moving into those low pressure areas above the mountains where that cold air kind of sits and moves in. So it's that hot air kind of moving over the top from those desert areas. Okay, so we're just going again high to low, but this is a big risk factor when you live down in these areas in LA, Santa Barbara, and things like that. That can cause really warm, dry winds that can really cause damage if a fire were to start. So Santa Anas, if you ever lived down there, you probably heard of the Santa Anas. That's that desert wind coming from our, the Great Basin on the other side of our Sierra Nevada mountain range, on the San Gabriel and San Bernardino mountains, that kind of rise up and go over and through those areas. Okay. Here's a little rundown of kind of how the Santa Ana works. So desert winds originate in a clockwise flow of air around the high pressure system east of the Sierras. So we have that high pressure, hot air. Okay, air extends from the mountains and is compressed, warm, and becoming less humid. This lowers the humidity, dries out vegetation, and can fan existing fires. Exactly. Winds squeeze through canyons. So because we have that topography, that wind is going to be moving through those canyons 40 to 60 miles an hour, and they do get very strong. They're very turbulent as far as for flights and things like that as well. Okay, so tomorrow we'll talk about temperature and precipitation. We're going to stop here today. I think that's enough. So finish your notes. We're going to summary for the first part, and then tomorrow I'll have another screencast for the rest of weather. Okay, thank you.